So, how are you today? Okay. Greeting to everybody from Bangkok, Thailand. Okay. Well, these topics, I'm going to be talking about the YY connections in three-phase system. Okay. There are, parameters that we need to deal with in these topics. Okay. So, I'm going to give you the parameter first, the name of the parameters. First, it's the I phase. Okay, so phase current. Okay, phase current. So current that go through each phase of the system. Okay, then there is a VP, phase voltage. Okay, so it's a voltage from each phase. Okay, another one is line current. Okay, so it's a current in running in the line, linking the source and the load. And another one is, of course, V line voltage. Okay, V line. So it's a voltage between the lifeline of the three phase. For example, if I have the Y connected system, right, like this. Okay, this is N, right? A, so this is A, right? B, right? And C. Line A, line B, line C, and line N neutral. Okay. And of course, we have this one, this is N, right? Node N. So this is VAN, right? VBN, and VCN. So therefore, VAN, VBN, and VCN, in these configurations, we call it the phase voltage. Okay. The current at each phase, right? So like this, right? IP. So this is I phase. So phase current. Okay. Phase voltage, phase current, right? Next one is line current. So line current, it would be the current in a line. So I line like this, I line A, I line B, I line C. Okay. So I line A, I line B, I line C are the line current. And the last one is the line voltage. So line voltage will be the voltage between lines. So it will be between line A and line B. So VAB like this. Between line B and line C. So VBC. And between line A and line C, VCA. Okay. So therefore, VAB, V between line B and line C, and the voltage between line C and line A, these are called the line voltage. So these are the four parameters that we will find in the three connections: YY connections, Y delta, delta Y, and delta delta connections. Okay, and today we're going to start with YY connections. Okay, so in general, the YY system, so YY system, okay, would consist of the following. elements. Okay. So this is the source. Okay, and with the source there's an internal impedance. This, so this is N, this is VAN, okay, VBN and VCN, okay, and this is called ZS, okay, and there is also impedance for the line, even for the neutral line. So this is ZL for line. Okay, and of course then there is the load, actual load itself. Okay, so ZL, as in ZL, okay, this is line, oh no, line and load, okay, there is ZS, which is the internal impedance, so ZS is the internal impedance, okay, ZL, the small l, okay, is the impedance of the line joining the phase of the source and the phase of the load. So ZL is the impedance of each line, okay, and Z capital L itself is the impedance of the load at each phase. So impedance of the load on each phase. Okay. However, what we are going to do in just this beginning course is that we will assume that ZL, the line, the small l, the impedance of the line, and the impedance of the internal impedance that come with the source, okay, are very small. Okay, when compared with the load, so therefore most of the time, okay, at the beginning now we're going to simply, okay, ignore, okay, those impedance, okay, and we're just going to so-called have just the source VAN, okay, VBN and VCN, like this, right, and oops, okay, so ZL, okay, and that's it. We're going to deal with that, okay, and of course this is I line, IA, right, this is N, IN, this is IB, and this is IC, okay, so, right, so that's what we're going to be dealing with. Now let's see, we're going to find, right now we need to find I line. So I'm going to start, okay, to find what is the line voltage, the line current, the phase voltage, and the phase current for the YY connections, okay, right, so let's start. This picture is a bit confused, so I'm going to redraw it, make your life easier to see. so YAN, YCN, YBN. So this is N, this is A, transmission line, okay, B, right? So I'm going to do it like this. C, my N, I'm not doing this very well. Okay, hold on. It does look like Y to me. So let me redraw this. Ta-da. Ta-da. So something like this. Okay. So Y, no? Y connections. Okay. So let's call this ZA, ZB, and ZC are your loads. And of course they are balanced. They are balanced system. So if they are balanced, that means your ZA is equal to ZB equal to ZC, right? On this side, okay. And if on the source is balanced, it means that the magnitude is the same, right? The magnitude of the same, and they are 120 degrees apart. So we're going to assume that now we're going to have a ABC sequence or positive sequence. I explained that on the last topics, okay? What an ABC or positive sequence is. So what it is of course, it means that your phase voltage on the generator side, okay, R, right? So VAN is equal to some amplitude V phase, 0 degrees, okay? VBN is equal to the same magnitude, but the angle is minus 120 degree volt, and VCN is equal to V phase with positive 120 degrees volt. Okay, so these are the phase voltage. So I'm going to find line voltages. Okay, so what are the line voltages for these YY connections? Okay, so my line voltages are, right, voltage between line A and line B, okay, voltage between line B and line C, and voltage between line C and line A. Okay, so using KVL, right, VAB is, I always tell my students, VAB means that you're walking from point A to point B. Okay, you're walking from point A to point B. So I'm going to walk from point A is right here, right, and this point B is right here. So as I'm walking along to go to my destinations, right, I come here, I walk all around here, I see positive sign first, right, positive VAN, okay, positive VAN, I'm going to be, right, so go back up here, right, and I see negative VBN, so I see positive VAN, right, and then minus VBN, then I reach my destination B. So VAB equal to VAN minus VBN, okay. So if I substitute it back in, so V phase, right, my VAN is V phase 0 degrees minus V phase VBN is angle minus 120 degrees. Okay, so if I do that, I would get V phase 1 plus a half plus J root 3 over 2. Okay, and my answer at the end would be VAB equal to root 3 V phase, and the angle is 30 degrees volt. 30 degrees volt. Okay, that's my VAB. right? So if okay, if I go on, next VBC, right? My VBC, if I walk from B to C, I walk from point B destination to point C, I see positive VBN minus VCN. So it becomes VBN minus VCN. So equal to, you do it right, this is VP minus 120 degrees minus VP plus 120 degrees. And the answer, VBC, would turn out to be root 3 V phase minus 90 degrees volt. Okay. If next VCA, walking from point C to point A, you see that you will pass VCN and then minus VAN. So it becomes V phase plus 120 degrees minus V phase, the magnitude, and 0 degrees. And the answer, VCA, would be equal to root 3 VP. Angle is minus 210 degrees. Okay. Or root 3 V phase plus 150 degrees volt. So if you list it out, your phase voltage is VAN equal to VP 0 degrees volt, right? VBN equal to V phase minus 120 degrees, VCN equal to V phase positive 120 degrees volt. Okay, and you will compare it to the line voltage that you calculated out. You see that VAB is equal to root 3 V phase 30 degrees, right? VBC is root 3 V phase minus 90 degrees, and VCA is equal to root 3 V phase, right, plus 150 degrees. Okay, let's see, can you draw any conclusions so make your life easier? So you end up seeing that, okay, for the line voltage, this is like your reference, right? Your reference, because you got this from the problem. Okay, you need to calculate line voltage. What happened is that the magnitude of your line voltage, they are the same because they are balanced systems, so they are the same, okay, for all three cases. But the value changed, right? The value changed such that, okay, the magnitude of the line voltage becomes root 3 times V phase. Okay, root 3 times V phase, right? So the magnitude of V line, okay, is root 3 times V phase. Okay. Now what about the phase angle? The phase angle, okay. The first value is VAN is 0 degrees, right? But V line, the V line, is plus 30. So it's 30 degrees ahead, right? 0 plus 30 is 30, right? 0, let's see, 0 plus 30 is 30. Look at the second one, VBN. Minus 120 plus 30 is equal to minus 90, right? Okay. And 120 plus 30 is 150. So everything, right? V line leads V phase by 30 degrees. So another conclusion is line voltage leads phase voltage by 30 degrees. So these are the two conclusions. See that? Okay. Also, one way to make your life even easier to do it in the exams, okay? You know that this is a balance system, right? You calculate VAN by maybe your calculator. You get this answer first, right? So you get this one answer here from the very beginning, from your calculator. But you know that it's balanced. So it's balanced system, that means that the magnitude are the same and the phase angle are 120 degrees apart from each other. Well, of course, here it's proven already that the magnitude is the same, right, on 3 of them. Look at the phase angle, right? If you look at your so-called reference phase voltage, from the first one to the second one is 0, right? And you subtract minus 120, right? So about this one, see? If you have 30 minus 120, you get minus 90. Okay. How about from the first VAN to VCN? From VAN to VCN, you plus 120, right? 0 plus 120 is plus 120. So look here, 30, you start with 30, right? 30 plus 120, you get 150. So they are also 120 degrees apart. Apart at how? Apart of, based on what your phase voltage was. So in this case, ABC sequence. Okay, so it's the same thing. See? So that's what it is. Okay, how to find line voltage. Now, how about phase current? Phase current and line current. Phase current and line current. So let's look at this configurations, back to this YY configurations. Okay. Now, we have found, we know V phase, right? VAN, VB, and VCN. We know also the line now, right? VAB, right? VAB, VBC, and VCA. Okay, those line voltage. Okay, so let me take it out first. Okay, now, let's, sorry. Hold on. I want to get rid of my I here. Nope, doesn't work. It's too tiny. Okay. Well, these lines. Now, phase current. Let's look at phase current. Phase current, right? Current come out from the source, right? From this phase. Current come out phase, I phase. Okay. Then it goes through here. Oh, okay. It's also line current. It becomes line current. And then it continue flowing. Oh, it's also the current that goes through this, impedance ZA on this phase, the phase on the load side. So that means for YY connections, I line is equal to I phase. I line equal to I phase. So what is the values then? Okay, the values. Well, from here, if just from VAN, you don't know how to find it, right? Just from I line, I don't know also what are the connections. But then it's the same thing as a current going through this ZA, the impedance ZA. So of course, IZA, right? I that go through ZA, this IZA, right, would be equal to the voltage drop across ZA, right, divided by ZA, like Ohm's law. I equal to V over the impedance, I equal to V over R, So the question is, what is V drop across ZA? So V drop across ZA must be, right, the current will come like this, so the voltage drop is positive, negative like this, so VZA is here. Use your fingers. One pointed here, the positive, right, side of the VZA, and another one at VZA, which is N, right, node N. If you trace it, back like this, I can't do it both hands. I can't show it. So you go like this. So the N goes along with N, right, go up until the source N, and point A here goes like this. Oh, so it's between this point and this point. So it's VAN. So therefore, IZA is equal to VAN, the phase voltage VAN divided by ZA. And of course, you know VAN from the problem given to you, right? Which is V phase 0 degrees divided by ZA. So you can get both the line current and phase current from this formula. Okay. So therefore, we can write it as, right? So therefore, I line AA, right? Line AA from point A to point is simply equal to VAN over ZA, right? And I line BB is simply VBN over ZB, and I line VCC is equal to VCN over ZC. Okay. And you find out that the magnitudes will be the same, but the angle would be 120 degrees apart. Okay. Right, so this would be equal to, of course, V phase 0 degrees over the impedance ZA and some angle ZC, right? So it becomes I phase angle minus theta Z, right? This one would be V phase minus 120 degrees over ZB angle theta Z, so it's V phase, right, minus 120 minus the phase angle of the impedance, and this V phase over ZC plus 120 divided by theta Z would be I phase, the magnitude of I phase angle would be 120 minus theta Z. So they are 120 degrees apart. Okay. And amazingly, if you actually add them together, right? So IN, right, is equal to I line AA plus I line BB plus I line CC, and you get the result to be equal to, the line add up to become 0. Okay, if you look at this configurations, right, everyone come, so I go like this, right? So this is IBB, right, ICC, and this is IAA, right, IAA, right? So come here and IN, add it up, and it turned out to be equal to, it will be equal to 0. So therefore, if you have a perfect balanced system, the neutral, the current in the neutral line will be 0, and actually you can actually omit and neutral line can be removed, and you if you have the perfect balanced system. Okay. So therefore, this is how you calculate V line, right, line voltage, line current, and phase current for the YY connections. So that's it for the YY connection. Thank you. So see you in the next one for Y and delta. Bye.